Good morning to everybody. I'm Luca Braidotti and I will present the work Identification of Measures to Contain the Outbreaks on Passenger Ships using Pedestrian Simulation, developed at the Integrated Ship Design Laboratory of the University of Trieste. The current pandemic, first notified in December 2019 in Wuhan, had and still has a strong impact on the world economy. Considering the maritime sector, the cruise ship industry is widely the most impacted. Only between March and September 2020, a loss of over $50 billion have been estimated. Cruise ships are high-density, isolated communities, where often public spaces are overcrowded and many services are shared by passengers or crew members. Such a scenario makes ships prone to outbreaks and hinder their control, as shown by the case of Diamond Princess, who led to the no-sail order issued by US government. This scenario opened the need to define procedures and guidelines to assure safety on passenger vessels during a pandemic. Besides, new opportunities to make passenger ships layout more resilient to outbreaks are also required. And right now, there is a complete lack of such guidelines applicable during the ship design. In such a context, Industry 4.0 and Shipping 4.0 tools can be applied. In detail, in the present works, the application of pedestrian simulation is explored, with two aims: to detect the critical issues in ship public spaces and assess the countermeasures on existing ships, and also to test alternatives designed to make the ship's public spaces more resilient to outbreaks. This presentation will start from the background represented by current guidelines for cruise operations, then critical parameters affecting an onboard outbreak will be presented and used to define a classification of ship internal spaces. Then the pedestrian simulation tool will be introduced, as well as the process for its usage in the maritime environment. Finally, the process will be applied on a large cruise vessel, gaining some conclusions. After the no-sail order, national and international organizations immediately started the development of guidelines for a safe recovery of cruise operations. Measures can be classified into two main categories: pre-cruise preventive measures and onboard measures. The pre-cruise preventive measures are applied before ship departure. First, a risk assessment should be carried out and the preventive measures should be customized according to the current pandemic situation and passenger origin. It might be necessary to reduce the ship capacity and to arrange a segregated quarantine area. The crew should be trained considering the new procedures and regulations applied on board. Crew should be divided according to their mention and risk level of exposure to the virus. All the persons engaged in international voyages should be informed about the preventive measures and consent to the health status monitoring. Finally, the access on board should be limited. The onboard preventive measures and outbreak control include social distancing, public space management, cleaning and sanitizing, management of air conditioning systems, management, preparation and serving of food, use of personal protective equipment, managing of a suspected case. COVID infection can spread on board in three main ways: direct contact with persons, contact with infected surfaces, and air conditioning systems, although this last mode has been questioned by some recent studies. According to recent experience and the recommendations, the most important parameters that can foster an outbreak on a passenger vessel are the following. First, the density of persons. In fact, overcrowding is the main source of direct contact. So, the American CDC prescribed a minimum distance among persons equal to 1.83 meters. It drives to a maximum allowable density of 0.38 persons per square meter. The second parameter is proximity, which considers the type of activity carried out within a specific internal space. For instance, while eating, you cannot wear masks, and this increases the infection risk due to proximity. Then, there is aggregation, which accounts for the number of persons involved in an activity and their contact level. For instance, aggregation in cabins or shops will be considerably smaller than in a swimming pool or in a theater. The layout of internal spaces has also an influence on outbreaks, since it changes the personal behavior and movements between different ship's areas. It is designed according to several safety criteria, considering evacuation, firefighting, but currently not outbreak control. Finally, often air conditioning systems are not capable to ensure sufficient air exchange and filtering required to prevent infections. Recirculation is usually about 70%, and common air ducts serve multiple spaces on the ship. Considering the critical parameters, here a classification of ship internal spaces has been proposed. 3 levels have been defined: low exposure risk, highlighted by green color, medium exposure risk in yellow, high exposure risk in red. The parameters driving to this classification are summarized in the table. In the low-risk areas, there is no frequent interaction among passengers and between passengers and crew. Therefore, low-risk areas are mainly identified as stairs, corridors, and cabins. Medium-risk areas differ from the low-risk ones mainly due to the higher density, proximity, and/or aggregation. Hence, the main spaces classified so are public spaces such as restaurants, bars, casinos, theaters, then service spaces, lobbies, restrooms, and elevators. Finally, high-risk areas are the ones where interaction with suspected or positive cases occurs. In normal operations, only the medical zone is classified this way, but during an outbreak it might be insufficient, and an additional quarantine area should be fitted and segregated from the rest of the ship. This classification is important in order to apply the proper countermeasures in different parts of the ship, which impact also the setup of pedestrian simulations. Simulation is one of the key enabling technologies in the framework of Industry 4.0. In this work, Legion Pedestrian Simulation tool has been applied to the maritime environment. Legion has been developed for the infrastructure design to simulate the movements of persons inside limited spaces, such as stadiums, squares, city centers, expos, and so on. It is based on an intelligent agent approach to modeling pedestrian behavior. Simulations are carried out within microscopic models defined with CAD tools. Models include obstacles, ingress and egress points. A so-called origin-destination matrix defines the start and the final point for each agent, which moves between them according to the minimum effort principle, while interacting with the environment and with the other agents. Agent sections and paths can be customized by behavioral models. Typical examples are the definition of waiting spots and the definitions of specific paths. Considering outbreaks problem, pedestrian simulation can provide very useful information, such as maximum cumulative density of the crowd, level of service of the analyzed space, mean velocity and time of ingress-egress. In Legion, it is also possible to evaluate the maximum capacity of a space in order to assure social distancing. Here you can see the process to apply the pedestrian simulations to passenger vessels. First, the internal spaces should be modeled starting from the general arrangement plan. The ship is a very complex environment, so it should be simplified, removing all the non-necessary elements, such as movable objects. Then, person sections are defined according to the space type and purpose. The ingress-egress facilities should be modeled, as well as the points where specific activities are carried out. Preferred paths can be defined for a group of agents, and also delays can be introduced. In detail, person profiles can be defined according to the standard population defined by IMO for evacuation simulations. OD metrics should be also built up. Origin can be defined according to the day case described in the FSS code issued by IMO. Details can be retrieved by the escape plan of the ship. Destinations are more difficult to define, especially in the design phase, so specific assumptions are required, possibly based on the shipowner's previous experience. Additional actions or specific paths can be defined for a specific agent or group to better reproduce the activities of the people on board. Then, the simulations can be carried out and the result analyzed. If they does not highlight critical issues, the process can be stopped. Otherwise, alternative measures based on different simulation controls or alternative layouts can be again simulated until a satisfactory result is obtained. In this work, the test case is a large passenger ship operating in the USA and Canada. The ship has the main particulars provided in the table. Ship spaces have been classified according to the proposed scale as shown in the first picture related to the deck 2. Then, focus has been made on the restaurant located in the aft main fire zone. It has a standard capacity of 700 passengers with 25 dedicated crew members. Considering the standard day case, the number of passengers is reduced to 525. The restaurant has a single access in the four boundary of the space. Due to the large number of obstacles, only the tables have been modeled in the pedestrian simulator, discarding the chairs. Nevertheless, table areas have been increased by 50%. The first issue identified is related to passenger density. Applying the maximum number of passengers, as well as the one related to FSS code, the density exceeds the limits issued by CDC. Moreover, to reduce the proximity risk, social distancing should be applied. So, all the seats exceeding 4 per table have been removed. Besides, all the seats located at less than 1.83 meters has been removed as well. It results in a strong capacity reduction. The maximum number of passengers is now 287 instead of the initial 700. Then, the most critical phases have been analyzed. They are the entrance and exit of passengers in and from the restaurant. Some preliminary simulations carried out with free-moving agents highlighted an acceptable maximum cumulative density in several spots. So, we tested an alternative solution. The restaurant has been divided into sectors. Passengers are supposed to book the restaurant place and to fill first the farther sectors. At exit, the order is reverted. Moreover, agents are forced to follow specific paths that can be marked with signals. The process has been shaped to last no more than 10 minutes. Here you can see the results of the solution in terms of maximum cumulative density and level of service of the restaurant. The proposed entrance and exit process mitigated the critical issues. However, some bottlenecks are still present due to the single access of the space. This problem can be avoided only further reducing the restaurant capacity, but such a reduction has not been deemed feasible for commercial reasons. So, the only available option is changing the space layout, which requires a costly retrofit. So, it is unacceptable as well. In a new design, we haven't these constraints, so it is possible to propose some changes to make the space more resilient to outbreaks. An example is provided for the test environment. To avoid the congestion, an additional passenger entrance can be fitted in the area highlighted by the figure on the left. It requires the reallocation of 3 restrooms serving the main corridor, an electric cabinet and a store. On the right, a possible alternative design is proposed, limiting as far as possible the restaurant capacity reduction, which is reduced only by 8 seats. In conclusion, simulations have been proved once again to be a powerful instrument applicable even for preventing and control outbreaks on board. This work shows how pedestrian simulation can be used to identify the critical issues in existing vessels and help to define customized mitigation procedures. The results of this analysis can guide also the ship design team to review the ship general arrangement when it might foster an outbreak. Changes can reduce congestion occurrence, however, they have a cost that should be considered during ship design. In general, layouts designed to be resilient to outbreaks are more space-consuming, thus, they can affect the economic performance of the ship. It means that, without a proper mandatory rules, they are not easily applicable. Thank you for your kind attention.